Eric Lanask. We're here in Santa Clara, California for our Editors' Days. I'm with Christina Richards from AOptix. Christina, thank you so much for joining me. It's a pleasure having you.
Great to be here.
So, we're talking a little bit about AOptix earlier, and I think it's important for folks to understand a little more about the technology that you're working with, that you've developed, because it's a little different than some of the other wireless technology that's out there.
You're absolutely right. It's very unique technology, and it's something that really hasn't been done in the wireless space before. And there's kind of three things going on, three technologies in play. You've got the two transmission technologies, which are things that people would be familiar with. Millimeter wave, it's a very tightly steered version of millimeter wave, and advanced optics, similar to free space optics, but with curvature adaptive optics mixed into it. So you've already got two robust wireless technologies working together. But it's a point-to-point line-of-sight transmission, and so both technologies are transmitting the same 2 gigabit data stream over that point-to-point. And at the receive side, this is where the third technology comes in. It's called dynamic packet resourcing, and what it does is it takes the data from either side of the stream and monitors it in real time. So you're taking the best bits of data from each side, and this gives you a much better output stream than you could get with either wireless technology by itself. So now you've got a wireless technology where you can get greater capacity. It's a 2 gig product, and we have a roadmap to 10 gig and 40 gig. You've got greater distance than you can get with some of the other larger capacity wireless units, up to 8 kilometers. And you've got greater availability that you can get from the other wireless technologies. So if you need a solution for where you can't trench for fiber, a fiber replacement in wireless that needs over a gigabit of capacity, 8 kilometers of distance, and carrier grade availability, you really only have this solution.
So what kind of use cases are we talking about?
So there's actually any place where you could put in fiber would be a use case for us, but there's three that we really focus on. And mobile backhaul is absolutely our most heavy focus. So this is basically, as people roll out 4G, LTE, and LTE Advanced, you're starting to need bigger capacities at individual cell sites. Before, we have about 50%, let's say in the U.S., we have about 50% of our cell sites covered by fiber, but then you've got the other 50%. And up till now, they've been able to be serviced by microwave because you haven't needed the larger capacities yet. As we roll out 4G LTE, you're going to start to need greater and greater capacities. And when you get to that point, you're starting to hit a capacity limit with microwave. You could put in millimeter wave, standalone traditional millimeter wave, but it's not going to get you beyond about 1 or 2 kilometers with any real robustness. So most macro cell backhaul radiuses are in the 5 to 8 kilometer range in the United States, in the urban and suburban areas. So in those locations, you need a wireless solution that can help you make the connectivity happen for sites that aren't ever going to be reached by fiber. So that's the biggest play for us. Another application that we've spent a lot of time in is in the financial services industry. And this is basically because it's a very low latency product. There's three ways that this product reduces the latency over a connection compared to trenching for fiber. One of them is the actual physical distance. When you trench in the ground for fiber, you're always going to have to go around obstacles and a different, like a rock formation, you hit bedrock, you have to go around it. So your physical path is going to be longer. That gives you more latency there. There's latency that's introduced by the unit itself. We have a very low latency within the box itself as opposed to other optical devices. And then there's the latency that is introduced by sending the infrared light through glass versus through the air. There's actual latency that's introduced if you're using glass as a transmission medium as opposed to an air transmission medium, which is what we do. So you add those things together, it gives you a very low latency product. And this is really important today. We're talking, on the order of nanoseconds of difference, right? Today, this only matters for the financial services industry. And so most recently, we did a connection between NASDAQ and BATS. So the two stock exchanges have a 26-kilometer link. It's multiple links, daisy-chained together to give them this really low latency connectivity, and that's very valuable from a trading perspective. Now, right now, that level of latency at the nanosecond level doesn't matter from a wireless perspective, from a mobile carrier perspective. In the future, it may, though. If we think about 5G, they're starting to talk about what 5G really means, right, in terms of capacity. And one of the things is certainly latency, as
Sure.
we're trying to push, large amounts of video through through the 5G network, ultra high definition video. Latency is going to start to become a very real challenge, and so in the future, I see that being valuable as well. And there's one other application I'm going to tell you about.
Sure.
So, and this is in last mile access, and this is actually not something that we've spent a lot of time in so far. But as we build our 40 gig product, we see this becoming a much bigger space for us to go in. And last mile access can mean a lot of different things, but really we're just talking about connecting those last 1 to 10 kilometers. How do you get that gap closed? And some of the situations that we've already deployed in that are kind of an example of what that would look like. There's a university that we've connected for video streaming of their classes to a remote site. And this is their last, I think it's a 5 kilometer link that they have there. There's also an example in Hong Kong. We're working with Top Express to do a connection between multiple villages. And in this case, you're actually going over water. So they would like to trench for fiber, but they can't because it's shipping lanes and you can't push it through. So their last mile access as well is what we're serving in that situation.
Really interesting stuff. Now, what about, eventually you've got wireline operators out there who are just, they're existing, not fiber networks, but, their copper is just not going to be enough to get us what we need. I mean,
sure.
Maybe we're there already. Do you have the potential here to let those operators go with wireless instead of having to lay new fiber?
Well, I think that there's always going to be a place for fiber in wireless networks and any type of service provider networks. So I see us as a complement to fiber. We are the complement for when you're going into locations where it's not economically doesn't make sense to lay fiber. You can't get the right of way. You can't pass through a certain area, like for instance with the shipping channels.
Okay.
But I think that our biggest play is being a complement to that fiber structure, and also fiber redundancy. That's a big thing that a lot of our customers have come to us with. Is even when they have 2 fiber paths, it's usually on the same physical conduit. So if that one physical conduit gets clipped, then they're out of business. So their redundancy, all of a sudden their business continuity plan is out the window. One of the companies that we've been working with, a healthcare company that's based in California, they want to get more robust redundancy for their fiber connections because right now they're running 2 paths over the same physical conduit. And this is one of the few technologies that could actually give them the amount of capacity that would make sense because they're doing genomic sequencing and imaging like MRIs, large amounts of data that they're trying to push through. You're just not going to be able to push that over a microwave link.
So there are going to be certain applications that really are going to benefit. What about from a cost perspective when you compare your solution as opposed to even if you can lay fiber? Is there a difference?
Yeah, there's definitely a difference, and there's actually a really great Ovum white paper out there that kind of lays out the detail on the cost savings. And compared to fiber and millimeter wave and microwave, we are laser radio technology is the lowest cost per gigabit in the United States as far as deploying a technology of any kind for mobile backhaul. When we look at our product compared to trenching for new fiber. And this is mostly in urban areas where you're going to have a higher cost for trenching fiber, then you can usually get a return on your investment in 9 to 12 months compared to trenching for new fiber. And so when you actually look at the cost value of putting our product in versus trying to trench for fiber, there can be a really good trade-off there in terms of getting a lower cost to put your network in place, plus just the flexibility issue, right? Because trenching for new fiber it's difficult to get right away. Here in California, it can be a year before you can get the okay to put down new fiber. So if you're in a situation where you need fiber capacity, but you can't get it in place, then this is definitely a solution for you.
Very cool. Exciting stuff. Thank you very much for sharing with us, Christina.
Absolutely.